Hi Math 95. In this video we're going to do a preview of section 9.1 where we're going to be working with linear inequalities. We won't be doing the business applications portion of this section. We'll just be working with the linear inequalities. So you may be familiar with linear inequalities. You may have worked them before. It just might have been a while, or you may have seen them fairly recently in some of your other math courses here at Lane. So let's just work through reminding ourselves a little bit about notation. So we've seen this kind of interval notation before, maybe. You may not have seen it if you've been strictly working with like inequality notation, which is what is found inside of what's called set builder notation. Okay, so without the squiggly brackets and the little x and vertical bar, you have seen interval notation like this, where x is larger than a and x is less than b at the same time. This is a compound inequality right here. And we have these different ways of denoting the same numbers. So for example, the idea here is that we're able to represent a part of the number line, or all the numbers that live between a and b, not including a and b, by this kind of notation here with the round brackets on each end and shading in between a and b. And another way we can denote that is by using either interval notation or set builder notation. Interval notation says that this is the interval a to b, right? And instead you can make use of what's called set builder notation, which says I'm going to describe those numbers living between a and b as a set, and so it's going to be a set, squiggly brackets, of x's. It's a set of x's. The vertical bar just means such that. So it's the set of all x's such that x lives between a and b, but it can't equal a or b. Notice there's no inclusive parts on the little inequalities there. That makes sure that we do not include the endpoints. You may also have seen the same thing with open circles at the end instead of the parentheses versus closed-in circles for the brackets, which is what the next interval denotes here. So just if you like at this moment, you might want to pause the video, right, so that you can make use of the time to look through the different ways we describe the intervals here. The first four are strictly intervals that are sort of not going off in one of the directions, like with arrowheads on the end, right? They're closed intervals here. So those first four are strictly written as this, right? Compound inequalities. The last ones are when we now allow the interval to sort of go off in one of the two directions this way, either all the way to the right or all the way to the left, or in both directions as in the last one, right? So this last one says it's the interval negative infinity to infinity, and in set builder notation it says the set of all x's such that x is a real number, which really means x can be any real number, and that's why we are saying the entire real number line here. Okay, so again, pause the video if you need a few minutes to look through these interval notations with their set builder notations and their corresponding graphs. So let's look at an example of working with what's called a linear inequality. So let's graph the solutions of each of these following inequalities on a number line, and then we'll use set builder notation to write the answers. So in this first one we have the linear inequality x is greater than -4. So the solution here for this one shows that, well, we want to write all of the x's that are larger than, strictly larger than -4, but not including -4. Okay, so the solution here is all the numbers that are greater than -4, and they're graphed on the number line by shading all the points to the right of -4. To the right, why? Because those are all the numbers bigger than -4. Okay, we don't include -4 here because it is not included in the inequality here. You could have also used an open circle at -4. Open circle meaning not shaded in. So let me show you what I mean by open circle. You could have instead shown this by saying open circle at -4 and then drawing the arrow to the right like that. In terms of set builder notation, we have the set of all x's such that x is greater than -4. Or in interval notation, starting at -4 but not including, right? Not including means this round parenthesis here, not a bracket. Round parenthesis -4 to infinity, right? So all values of x greater than -4. Let's think about the second one here. So if we're looking at -2 to 7, right, we want all the values of x that are bigger than or equal to -7 and less than, I'm sorry, I said that backwards. All the values of x that are greater than or equal to -2 and at the same time less than 7. I should have maybe taken a nap before starting the video. I'm a little bit tired today. So let's see, if we were going to graph this on a number line, that means we have to shade all of the points that are larger than 2 or equal to 2, hence the closed bracket here, but at the same time also less than 7. So we don't just continue this little red line on and on and on. We don't want to go past 7, and we also don't want to include 7 because it's not included here in this inequality. Okay, another way to have done this would be to use the closed circle and open circle notation. So you could have done a closed dot at -2, shaded all the way up to 7, and then done an open circle at 7, right? So some people may have seen it that way also. Set builder notation would say the set of all x's such that x is greater than or equal to -2 and less than 7. Okay, and so in interval notation that would be bracket -2 to 7. So just a couple of reminders about properties of inequalities here. In general, what this is saying is you're allowed to add or subtract a number to either side of the inequality. This is the same thing that we've had for our work with equalities or equations. You can add or subtract the same thing from both sides, and it doesn't change the inequality. You are allowed to multiply or divide by numbers on either side of the inequality as well. Just one thing you have to be careful about. So if we multiply or divide both sides of an inequality by the same positive number, the result is equivalent to the original inequality. So the inequality won't change as long as you multiply or divide by a positive number. However, if we multiply or divide both sides of an inequality by the same negative number, what we have to do then is reverse the direction of the inequality. So for example, here, if we have -4x is less than 20, in order to get x by itself, you have to do what? You have to divide by -4. But whenever you multiply or divide an inequality by negative, you have to reverse the direction of the inequality. Okay, so notice that the direction has actually been reversed once you apply the division by the negative, right? So here, it still is opening to the right. Once you actually have the division by a negative number there, it has been reversed, right? So that may not be intuitive for you that it should happen here, but once you've placed the negative in the denominator or multiplied by a negative, you should have already switched them. Okay, so just reverse the direction when you multiply or divide by a negative, and that's down here in this, this little summary thing. And it does this fun little spin thing just to make sure that you actually saw that how important that actually is, because a lot of people forget. Okay, so if we were going to solve a linear inequality, this means that we might have a complicated expression of x on one side and we want to get it just simplified down to being an x so we can sketch the solution on a number line. The first thing we should do is simplify the algebraic expression on one side, or on each side, I'm sorry, if you need to follow order of operations or perform out what parentheses are indicating, something like that. We can use the addition property to collect all the variable terms on one side and all the numbers on the other side, right? Move all the x's to one side, all the numbers to the other side, just like with equations. Use the multiplication property to isolate the variable, right? And remember to reverse the direction of the inequality if you multiply or divide by a negative. Finally, express your solution in set builder or as an interval notation and graph. So let's see if we can try an example. Okay, so let's solve this following linear inequality here and graph. Okay, so it looks like we do have some order of operations we should follow here. So let's first perform order of operations on the left. So I get 15 minus 5x less than or equal to 3x minus 1. We've performed all of the possible simplifications here. Now what we need to do is collect terms. So there are ways you can try to think about working with these inequalities so you can avoid multiplying or dividing by a negative. For example, I see that if I add 5x to both sides, then the number of x's I have over here will be a positive number of x's, right? So that might be a good thing to do so that we don't have to worry about later multiplying or dividing by a negative. So when I do that, I get 15 less than or equal to 8x minus 1. I'm going to add 1 to both sides. And I get 16 less than or equal to 8x. Now I'm going to divide by 8. Notice that's a positive number, so I don't have to worry about switching the direction of the inequality. So I get 2 less than or equal to x, right? Or the same way to write that would be x is greater than or equal to 2, right? Those two things are the same, notice. This says x is greater than or equal to 2. This says x is greater than or equal to 2, right? Same thing. So this is interval notation. In terms of set builder notation, we would write with squiggly bracket, set of all x's such that x is greater than or equal to 2. And then in an interval, we would write, well, we would say starting at 2, all numbers bigger than 2. That goes off to infinity. We want to include 2 because of the inclusive line here. We never do a bracket on infinity because infinity is an undefined number and we can never actually get there to include it. So you always just do a parenthesis. Okay, let's sketch on the number line. Okay, so here is 2. I want to say start at 2 and go all values bigger than 2, right? In that direction there. Good. So let's see, I think if I hit next, it's going to cover up my work. Yep, simplify, but you can go back if you needed that uncovered. And here is a sketch of theirs, much nicer than mine, of course. All right, so that's a quick preview of what you're going to see in section 9.1. One last thing to note is that we may want to just recall a couple of important things about, let's see, about solving linear inequalities. So here, solving a linear inequality is similar to solving a linear equation, except for two important differences. When you solve an inequality, your solution is usually an interval, not a point. Okay, usually you get a value of x if it's an equality, and for an inequality you get an interval. And when you multiply both sides of an inequality by a negative or divide, right, you have to remember to reverse the direction of the inequality sign. That is, pow. They like to say pow it, right? Point the other way. All right, so for now, that's a brief or semi-brief preview of what you're going to see in 9.1.